We're asked to conduct a chi-square test of independence here. So we're testing to see whether these two categories are dependent or independent on one another. And I think this is actually a table we saw earlier. Maybe the numbers have changed a little bit, but there's two categories. There's the student's choice in major in college. Oh, actually, this is a little different. The other one had athletes as one of the categories. So student's choice in major is one category, and then the other category is gender. So we're conducting a test to see whether a person's major is dependent on a person's gender. You know, it's not going to be directly dependent, but if sometimes it just happens that we find that more men are choosing one major than women, you know, for various reasons, and that's a whole entire class that we could get into on why that happens in society. Okay, yeah. So sometimes they're dependent on one another, which means men are just more likely to choose one major over the other. Okay, or maybe they're independent. Maybe men and women are selecting their majors, you know, without any sort of like bias towards one major or the other. Okay, there's those two possibilities. So when you conduct a chi-square test of independence, your null hypothesis, we start with like the no effect model, that they're independent. They don't rely on each other to be conducted. Or H1 or HA, I forget what Noon uses. The alternative is that they are dependent on one another. Okay, so let's see. The null hypothesis: the two variables are dependent. No, the two variables are independent. This is the null hypothesis. And then the alternative hypothesis: the two variables are dependent on one another. Okay. So we've got our null and alternative hypothesis. Now we've got to calculate the chi-square test statistic. That's going to take a little bit of time because we need to find the expected value for each one. The test statistic, oh, that's a bad chi-square. The test statistic is found by taking every observed value, meaning like the 16, the 6, the 20, take every observed value, subtract it by its corresponding expected value, square that difference, and divide by the expected value. Okay, so we need these expected values. And like we did in the previous video, the expected value is found by taking the row total times the column total divided by the grand total. So for this first one, the first expected value, I'm going to label this table. This is my expected value table. I'm going to take the row total of 42, multiply it to the column total of 24, and divide by the grand total of 86. Okay, 42 times 24 divided by 86. I get an expected value of about 11.72. And then just to make sure we're all on the same page, let me show you the full calculation for this, for humanities, for men that chose the humanities. The row total is 42. The column total is 26. So you multiply the row and the column total and then divide by the grand total. So 42 times 26 divided by 86, 12.7 we'll say. So the rest of these I'll just crunch out real quick so we can get to the next part. 17.58. Need some decimals because, oh good, we're going to have to just round to one decimal place, so we should take at least two decimals with us. For the women in the arts, it's again the row total times the column total, divide by the grand total, 12.28. Women in the humanities, row total times column total, divide by grand total, 13.30. And then women in the sciences, row total times column total, divide by grand total, 18.42. Okay, so now we can finally calculate the chi-square test statistic. It's going to be found by taking each observed value. So men in the arts, the observed value was 16. Subtract by the expected value that we just found for men in the arts, 11.72. Square the difference, then divide by 11.72. That's the first one. And then you've got to add it to men in the humanities. The observed was 6. The expected was 12.7. So square that difference, divide by 12.7, and then keep going in this fashion until you've done all of them, okay? I've done the first two. There's 6 in total. So I can usually do this quicker with a calculator. Let me type that out here. So my observed was 16 for men in the arts. My expected was 11.72. Square that difference, then divide it by the expected. So my first value is 1.563. Oops. And then the next one, for men in the humanities, I got observed of 6, expected 12.7. Square the difference, divide by 12.7. So 3.535. When I round. And then men in the sciences, observed was 20, expected was 17.58. Square the difference, then divide by the total. And then women in the arts, the observed was 8, the expected was 12.28. Square the difference, then divide by the grand total. So 0.213. Women in the humanities, observed was 20, expected was 13.3, I think. Might have lost a decimal there. Square that difference. That's a big one because we observed 20 for women. Oh, 13.3. Was that right? Square that difference. Oh, I forgot to divide by the expected. Oof. Okay, 13.3. That makes more sense. 3.38. Sorry. And then what do we got? Sciences. We observed 16. We expected 18.42. Square the difference. Divide by the expected. Hopefully I didn't make any mistakes there, because it's painful to go back and try to figure out where. So if you add all these up, that's your chi-squared test statistic. Oh. Got 9.077, so 9.07, we're going to round to 9.1. Cross our fingers. Oh no, what did I get wrong? Gotta check each. I mean, maybe by looking at it we'll be able to tell. I think men in the arts, I think I might have got that very first. No, I don't know. 16 minus 11.72. Square the difference. No, that's right. Divide by 11.72. That first one's right. The second one, 12.7. That was our. Oh, that's our expected, but it's not going to matter the order because we squared it, the difference anyway. But the observed minus expected squared, divide by the expected. 3.535. For the third one, we observed 17.58. We expected 20. Square that difference, then divide by 17.58. Oh, that one is wrong. The third one, this should be, miscalculate that, 0.333. While we're at it, let's see if old man Isaac got something else wrong. Square the difference, divide by the expected, 12.28. Man, I got this one wrong too. What was I doing? Women, so just a triple check here. We observed 8 women. We got 12.28 expected. Square the difference, then divide by the expected. That one down there should be 1.492. For women in the humanities, observed 20, expected 13.3. Square the difference, then divide by the expected. That one's right. And then for women in the sciences, observed 16, expected 18.42. Square the difference, then divide by the expected. That one's right too. Okay, so now that I fixed those two, what did you do? 10.621, so 10.6 is my corrected. If I get this wrong, I'm going home. 10.6. Phew. Okay, so yeah, I guess the lesson there is we got to be very careful with each calculation because then you got to go back and check everything. That's our test statistic. Okay, you add up all those squared differences, divide by the expected value. Okay, to determine the critical value, the degrees of freedom when you're conducting a chi-square test of independence is the number of rows minus 1, excluding the columns. Okay, don't count the column totals. Sorry, don't count the row totals. The number of rows minus 1, excluding the totals, times the number of columns minus 1, again, excluding the totals. So there are let's start with rows. There are 2 categories in the rows. There's 2 values for the category in the row. And there's 1, 2, 3 columns. So we got 1 times 2 makes 2 for our degrees of freedom. And the test, they wanted a 1% significance level, so we're going to look at 0.01 with degrees of freedom of 2. That lines up with 9.210. Degrees of freedom 2, 0.01. Yeah, that all matches up. And just like with all the other tests, you want to compare your test statistic to the critical value. Our test statistic surpasses the critical value, okay? Here's roughly a chi-square distribution. Our critical value is 9.2. Our test statistic is somewhere here, over here at 10.6. So that means we should reject HO. We're in the rejection region. At the 1% significance level, when you reject HO, that means you found significant evidence. The two affect each other somehow. They're dependent on each other.